So actually my talk will be about, because first of all, thank you very much for inviting me for this extremely multidisciplinary event. It's, I never saw in my life such kind of multidisciplinarity. Combination of polymer chemistry with poetry and probably some music later. Yeah, that is just fascinating and incredible. Since this is not about the science itself, but about the creativity in science, I just wanted to share with you one example of fruitful analogy, or as in poetry we would say, some kind of allusion, which would help us to do something real. So first of all, I will talk about the excitable systems. And the excitability is probably one of the fundamental features which we can attribute to living nature. Because we understand that if I will pinch this trigger, nothing will happen. If I pinch myself, probably I will be very excited. And we have a lot of excitable tissues in the living organisms, such as nerve tissue, skeletal muscle, smooth muscle, cardiac muscle, and as well, many biological systems may be described in terms of excitability in a little bit wider sense. This includes microbiological colonies, where we can regard the excited state when they actively multiplicate. Populations of different species, they're same or very similar. Initiations and spread of epidemics, etc., etc., etc. All these processes share very important similarity. They all involve signaling and action. So the combination of propagating signal with a local action as a response to this signal is very important to such systems, in a very simple description of that. In chemistry, these systems are known as activator-inhibitor systems, and in physics, a wide class of cooperative processes also can be regarded as these excitable systems. Actually, systems which can exhibit first-order phase transition processes. And two major organs in our body, brain and heart, are excitable systems. Why we can say that all of them are kind of similar, and what makes us to think about that they are very similar in different features? First of all, because if we will go to the basic mathematical description, then mathematics is a universal language of science and probably nature. We will have very similar equations, which are the reaction diffusion class of equations. And the simplest case fits Unaguma equation with a slight modification of the phase portrait of the system. We can have a variety of different kinetics. We may have excitable kinetics, we may have oscillating kinetics, we may have bistable kinetics, but just changing the intersection point of two null lines. And now we will focus on heart tissue. Because in heart, the signaling is electrical signal between cells which propagate over the entire heart mass, and the local action is contractile function of heart. So what happens if heart works normally. There is an excitation which spreads from the sinus node and it propagates toward the atrial node, and from atrial node through the his bundle and excites the muscle of the ventricle, and the ventricle pumps the blood regularly. What would happen if the coordination of this contraction in different fibers would be destroyed? All would all be different law, not the same rule which is imposed by sinus node. In this case, we may have something which is called spiral waves or re-entry in the heart, and eventually we may have a fibrillation, and it is shown in the last movie. There is a very irregular contraction of fibers, so the pumping property of the heart is crucially damaged. How actually the heart may come to this dangerous and chaotic state? This movie from the computer simulation showed the scenario. That's a normal propagation. Now, what happened? The wave was destabilized, wave breaks evolved into spirals, and eventually the spirals multiplied, and eventually we had a completely chaotic state of the heart. I'll show this again from the beginning. So this is dangerous situation. This is what is called fibrillation. And that is what for defibrillators are used. Normal propagation and the wave breaks. So our goal, if we want to fight this dangerous condition in the heart, our goal is to eliminate the conditions for the wave breaks, for the origination of the wave breaks and the origination of the spiral waves. And what is the problem? The problem is that seemingly it's so simple, but due to high nonlinearity of this problem, it's very difficult to have analytical theory of spiral waves, as well as computer simulations are very expensive and very time-consuming. And empirical description is not sufficient because, of course, cardiologists, they can just understand that there are some wave break, that there are some spiral waves or re-entries, as they want to say, which originate from them. But what to do? How to remove them? So what? The solution. The solution is analogy. Analogy, and this is a model system, what we call in physics model system. And many non-biological systems actually show excitable kinetics, as I mentioned before. They might be easier to handle. For example, so-called iron nerve system. If you put the iron plate or steel plate into the strong nitric acid solution, it wouldn't be dissolved immediately, but it would be first go through some dissolution, and after that it will be covered by naturally occurring protection film, which is called passivation film. If to locally disturb this film, it is possible to get the propagating pulse. And this is very similar to what we observe in nervous and in heart tissue. This is the steel plates submerged into strong nitric acid. These are my fingers in acid-resistant gloves. So, if to initiate the wave, it may show, I believe we can see something. It looks so dark to me. There's a propagating spiral wave system. All right. Is it a good model system? Unfortunately, no. It's not very stable. It's very fast. And a bit difficult to handle because it is a strong nitric acid. But there's another example. This is Bellows-Jabotinsky reaction, one of the most famous examples of auto-oscillating chemical reactions. In this beaker, the solution undergoes transition from red state to blue state. Red is a little bit extended, blue is a little bit fast. And this oscillation of color and oscillation of intermediate chemicals is very similar to what happens when we have an excitable cell, which can be excited and then comes back, then excited and comes back. If to spread this solution into the thin layer, we can easily observe excitation waves, which are shown in these two frames, as well as these waves may evolve into spiral waves if you have a wave breaks. Okay, so we choose as a model system Bellows-Jabotinsky or BZ reaction, because the ingredients for this reaction are relatively inexpensive. It runs at room temperature, and the characteristic time, which is important, this is not too fast, not too slow. So the wave pattern would develop within minutes, not hours, but also it's slow enough that you can record it easily and you can observe it and you actually can conduct experiments interactively. Even batch reactor without renewing the chemicals would allow to obtain more than 100 waves, which is very, very stable. But if you use the specially designed continuously fed open reactors, it is possible to have practically indefinite living wave pattern. If to use hydrogels and to put this reaction not simply into the thin aqueous solution, because the aqueous solution, okay, water, thin layer of water is very unstable. You touch it and you destroy everything. But hydrogels like agarose gel or polyacrylamide gel, they are chemically inert for this reaction and they keep it away from any hydrodynamic flows. And eventually, the photosensitive version of this reaction allows to change the parameters, which is, for instance, just excitability, extent of excitability in the course of the experiment and in arbitrary mean. So that was nice model system. And we started work with this system more than 25 years ago. And one of the first results which I got when I just defended my PhD, that we can actually synchronize spiral waves if we create in the system the wave source with a higher frequency than the frequency of the rotation of the spiral, and we can expel spiral, pushing it away, and it was published 5 years ago. Then, and really required about 20 or more years to introduce this concept to the cardiology. Okay, this just another examples of different wave patterns. So I want to stand there. So what we do now is a cardiomyocyte tissue culture, corresponding exactly to the very complex shape of the heart would be probably to the extent. So what we do, we produce the tissue culture from neonatal cardiomyocytes, which is relatively homogeneous and relatively anisotropic system. And then we can track these excitation waves in the system by using fluorescent dyes. And in this system, we confirm that high-frequency pacing may expel spiral waves. This is the experiment. Red is excitable state of the tissue. This yellow-blue is resting state of this tissue. And we have here the spiral wave was initiated. This size of this cover slip containing the cardiomyocyte tissue is 25 millimeters in diameter. And the basic electrode is located right here. So the scenario is like this. The spiral wave was initiated. We recorded it. And then started pacing from this pacing electrode with the frequency exceeding the frequency of the spiral wave. Well, just to make sure that we really expel spiral, we continued pacing for some while. We were very patient at that time. When eventually we stopped pacing, there was no spiral anymore. And of course, that's not a single experiment. It was just like illustrative experiment. We showed this in multiple experiments. So what this phenomenon can tell us? Actually, a lot. Sorry for a little bit of Japanese in this slide. So instead of application of the huge voltage and current shock, which actually damaged the heart, it is possible to apply just a sequence of physiologically relevant pulses with a frequency exceeding the characteristic frequency of tachyarrhythmia. And this sequence would expel these spiral waves. In fact, this phenomenon was empirically observed by cardiologists, but they didn't know why it happens. And now what we are doing, we are just creating the fundamental background for improving this procedure. And that is due to the analogy with the chemical waves.